Hello and welcome to this lecture. We're going to now start looking at how to describe joint distributions between two random variables. One of them is discrete, the other is continuous. What's the easiest way to describe it? I'll just propose one method. There are other methods also, but the method I'm proposing I think is most common, most useful, and simple to use. Right, in practice, it's simple to use. I sort of motivated this by giving you the iris data set and all that. But in this lecture, maybe we won't refer too much to the iris data set. We'll just describe a discrete random variable and a continuous random variable together in a joint distribution. How would you go about describing that? Okay. So how do you describe the joint distribution of two random variables? Let's say x and y are jointly distributed. X is discrete. It has a range Tx and it has a PMF Px. Okay, remember PMF x, Px is probability that capital X equals small x, right? So that's the PMF of a discrete random variable. Now, what will happen in these scenarios is, now y I know is jointly distributed with x. How do we understand the joint distribution? For every value that x can take, every small x in the range Tx, you can actually have a continuous random variable. I'm calling it y sub small x, as in if capital X were to be equal to small x, then y would be distributed like yx. Okay, so you can always say that. So you remember, you can go back to the iris class and the sepal width, sepal length picture that I drew there. If the class is 0, you have a certain distribution. If the class is 1, you have another distribution. If class is 2, you have another distribution, right? So you have 3 different distributions. Depending on the class, you pick one of these. So that kind of a scenario is what we will assume is always available to us. Okay, so this yx, we will give it a slightly different notation. We will think of that as the random variable y given x equals small x. Okay, sort of like a conditional random variable in some sense. And usual notation for this is y in the vertical line x equals small x. So y given x equals small x. So this y sub small x is this particular distribution that y is taking when x, capital X, has taken a small value, value of small x, that we will denote as y given x equals x. Okay, so this is common notation. Now, this density that we had, right? So the density, given that capital X became small x, we had one of these densities. That density also we will denote it like this: f y given x equals x of y. Okay, so that's the density. Okay, remember x has a PMF Px, and then y, for every value of x given x equals small x, y has a conditional density f y given x equals x. So this is a density, it's a conditional density. When given x equals x, this is the density for y. Okay. Now, if you want the marginal density of y itself, the entire density, you have to do this summation. Okay, so the summation over all values of x in the range of Tx, Px of x, the PMF of x, times the conditional. Okay, this is easy to see. This is the total probability law. This is sort of like the total probability law. All of these things have rigorous proofs and ideas of probability space and all that. We're not going into that much detail here, but hopefully you can see that these formulae are intuitive and easy to understand, right? So notice that this is like probability that x equals x. This is density of y conditioned on x equals x. So you multiply, add over all x, you should get the density of y, right? It's sort of reasonable in some sense, except that we're mixing up probabilities and densities. You might think, okay, maybe I'm doing something wrong here. No, it's okay. This description is a very comfortable and correct description for the kind of situation we are looking at. Okay, so there is a discrete and continuous random variable. They have a joint distribution which is described in terms of the conditional densities. Okay, so this picture is important to keep in mind. So this is how we will describe the joint distribution. Going back to the iris class and sepal length, for instance, the sepal length given the class equals 0 will be one continuous distribution. Sepal length given class equals 1 will be another continuous distribution. Sepal length given class equals 2 will be another distribution. And together, that describes the joint distribution of class and sepal length. Simple, right? Since it's easy, you'll see. We're starting at this point. We'll start doing some problems, and you'll begin to get more and more clarity about this situation as we do more and more problems. Okay, so here is a problem, right? So whenever you see a description, you should also do a problem. So let's do this problem. Okay, so this says x is uniform 0, 1, 2. Okay, so notice this braces here. So this braces here clearly indicate that this is a discrete uniform random variable. Okay, taking three values 0, 1, 2, and then y given x equals 0 is normal 5 comma 0.4. Okay, so this is y. So these three describe the conditional densities, right? So these are all conditional densities. Okay, y given x equals 0, y given x equals 1, y given x equals 2. So what the distributions are, okay, so this is normal 5 comma 0.4, this is normal 6 comma 0.5, this is normal 7 comma 0.6. Fine, I mean, this could be any other distribution also, just three different distributions. Maybe I should draw the three of them and then give you a sense of how they look. Let's try that. So let's look at this 5, 6, 7, right? So let's say 2x here, so maybe 5 is here, 6 is here, 7 is here. So this y given x equals 0 is 5 comma 0.4. 0.4 would be low variance guy, so go a little bit higher and then maybe fall off a bit faster. I don't know if this is correct or wrong, but anyway, this is how it will look. This is normal with mean 5 and variance 0.4. So this n is a abbreviation for normal. It's a very, very common abbreviation. I'll also use it quite often. I mean, it's difficult to write normal all the time, so I'll just write n. And then you've got normal 6 comma 0.5, so slightly higher variance, so it will go a little lower and then a bit wider. Okay, maybe not this much wide, so I'm not drawing this to scale. I'll expect that if you can do it on some computer or something, you'll get a better thing. So this is normal 6 comma 0.5. Likewise, this normal 7 comma 0.6. So this will go a little bit lower, and then maybe something like that. Okay. So this is normal 7 comma 0.6. So each of these things is the conditional distribution of y given x became 0, x became 1, and x became 2. Okay. Sort of like the sepal length if you want. Okay. So this is the different distributions. So this is, okay, I shouldn't say this is x, this is y, I'm sorry. Okay, so y given x equals 0, 1, and 2. Okay, so now how do you do the marginal? So fy given x equals 0 of y is the density of normal 1 by root 2 pi into 0.4 e power minus y minus 5 whole squared by 2 into 0.4 squared, right? So this is y given x equals 0. Likewise, you can also write y given x equals 1 and y given x equals 2. I'll leave it as an exercise for you to write this. It's easy, right? Instead of 5, you have to put 6 here. Instead of 0.4, you have to put 0.5 here for x equals 1. Likewise, for x equals 2, instead of 5, you need to put 7 there. Instead of 0.4, you should put 0.6. Okay. So what I'll do is I'll write the distribution for y. So this is going to be sum over every value of x in the range, right? So x in the range of x, it's 0, 1, and 2. Probability that x takes value 0, that's 1 by 3. It's uniform, right? So 1 by 3 times 1 by root 2 pi times 0.4 e power minus y minus 5 squared by 2.4 squared plus 1 by 3 times 1 by root 2 pi times 0.5 e power minus y minus 6 whole squared by 2.5 whole squared plus 1 by 3 1 over root 2 pi 0.6 e power minus y minus 7 whole square 2 times 0.6 whole square. Okay, so this is the marginal distribution of y. Okay, remember the conditional densities are all Gaussian, but the marginal is not Gaussian. Okay, so this is not Gaussian. Gaussian cannot have three different peaks and their average. This kind of a distribution is called a mixture Gaussian. Okay, so this is called mixture of Gaussians. So this is a mixture of three Gaussians. Mixture of Gaussians or Gaussian mixture of or mixture Gaussian. This is commonly used. So this is a very actually it's quite a popular model. The Gaussian mixtures quite often in practice. These end up being very popular. Okay. So notice the second question. The first question was easy enough to answer. Like I said, it all starts very small, basic definition. This seems easy enough, but there's always a next step, which is slightly more complicated. And that's where we'll go next. So what will happen usually is some sort of a reverse question, right? You start with x, and then you give conditional for y given x, and then you plot the marginal of y, etc. All that seems easy enough to do. What about the reverse? Okay, you observe a y. Okay, you observe that your capital Y is around y naught. Remember, this is continuous, right? So we're not trying to be precisely equal here. We're just around y naught, let's say. Okay, y is around y naught. What can we possibly say about x? Okay, so that is a question of interest here. So that's sort of like the classification problem with irises, right? Supposing you saw that the sepal length was this much. Okay, what can you say about the class of the iris? Okay, is there anything you can say at all? That's the sort of classification problem. So you can see the second question I'm asking is going in that direction. Okay, so that is where the interest comes. So it becomes a slightly more twisted reverse problem. And how do we do that is the question. So we will invoke something like a Bayes theorem in this continuous discrete combo framework and try and answer that next question. Okay, so for answering the next question, I'm not going to answer it immediately. I will describe one little method and then come back and think about how to answer that. So you can just look at this picture. If y were to be around 5 or 4 or 3 or much lesser, you're going to probably say the class was 0, right? If y were to be around 8 or 9 or even 7, 7.5 or something, maybe you're going to say the class is likely to be 2. But what about if y were 6.5, right? What are you going to say is the class? So, right? So these kind of questions are interesting, right? So this is at the heart of how data science works, how statistics works. So it's important to understand how to answer these kind of questions. Okay. So let's see how these kind of questions can be answered. Okay. So what we are after is some sort of a conditional probability for the discrete random variable, given that the continuous random variable took some value. So you have a discrete and continuous random variable that have a joint distribution, which we have described as before. Discrete, given every discrete, you have a conditional for the continuous. Okay, conditional density for the continuous. Now I want sort of the inverse problem, sort of the Bayes rule sort of equivalent. What is the conditional probability for the discrete random variable taking a particular value, given that the continuous random variable took a value somewhere around something? Okay. So here again, one can prove these formulae very carefully from basic theory and all that. We are not going to do it. I'm going to basically state it as a definition for you. You'll see it's a very intuitive, simple definition, and most of you will immediately accept it. So it's okay. We don't have to see a rigorous proof. So proofs for such statements can be found in textbooks. I can refer you to them if you're interested. Okay. So let's see what the statement is. The statement is much more important to understand and use. Okay. So let's say x and y are jointly distributed, with x being discrete, having a range tx and pm of px. And there are these conditional densities that are given to you. F y given x equals x of y, each of them is a density. Okay, so the conditional density. So the conditional probability of x given y equals y naught. Okay, so now notice this y equals y naught is very troubling. A lot of people get troubled by that because we know the probability that y equals y naught is 0, right? Right? We know that y is a continuous random variable. Probability that y equals y naught is 0. So why am I saying y equals y naught? It turns out it's okay. In the conditional case, in this particular case,
you can condition on y equal to y naught. Okay, so again, the theory there is a little bit more complicated. If you really want to be very, if you want more intuition, simply think of y taking values around y naught, and for convenience, we're simply writing it as y equals y naught. Okay, so that's also not too bad. Okay, so here's the big formula, and I'm stating this is definition. This is actually, you can prove this. This is, you can write this down and prove it. It's not very hard, given, we not say it's not very hard. It's technical, and you have to write down probability space equations and all that very carefully. You can write it down, but let's just accept it, right? We'll move on. Okay, and it's very intuitive. You'll see why it's intuitive. We'll say this once again. So here's the formula. Let's first understand the formula. Probability that capital X equals small x given y equals y naught. Okay, this is equal to the PMF of x times the conditional density Fy given x equals x of y naught divided by the marginal density of Fy evaluated at y naught. Okay, so you have a density in the numerator, you have a density in the denominator. Okay, the numerator density is the conditional density, denominator density is the total marginal density, and then you have the Px of x multiplying Fy. Remember, this guy is actually what? Sum over x and dx, Px of x, Fy given x equals x of y naught. Okay, so this should remind you of Bayes' rule, right? This is very much like Bayes' rule. This is the, conditional total probability dividing, except that you don't have only probabilities, you have these densities coming in. But that's okay. You have density in the numerator, density in the denominator. Sort of, if you go to the limit, things should be okay, and you get a probability out as the answer. Okay, so the best way to remember this formula is to think of the analogy to Bayes' rule. Okay, so this is very, very similar to Bayes' rule, except that, so normally how do you write Bayes' rule? So you write Bayes' rule as probability of A given B times probability of B equals probability of B given A times probability of A. This is sort of how you write Bayes' rule, right? So notice here we have A being x equal to x, okay, and then so B is sort of like B is sort of like y equals y naught, right? That's what you have here. So wherever you have a discrete random variable, you're going to have probability of x equals x given y equals y naught. And wherever you have a continuous random variable, you just smoothly go to the density. Okay. So you notice here this probability of B is going to be, of course, 0, right? It doesn't make sense there. So you just move into the density. And likewise here also, B given x equal to x is again, probability wise it's going to go up to 0, but you can move to the density, and then this equation would be valid. Okay, so it's sort of like Bayes' rule, with the densities conveniently replacing wherever you have probabilities for continuous random variables. That's also true. Okay, so this is how one evaluates this conditional distribution of the discrete random variable given the continuous random variable is jointly distributed. Okay, so this is a very nice and interesting little formula. It's very reminiscent of Bayes' rule. I would just think of Bayes' rule as the basic thing, and then use this formula. A lot of you may be thinking Bayes' rule is already confusing, and this is now added confusion with discrete and continuous, but this is a very, very commonly occurring phenomenon. Many models you want to use this idea, so it's good to get a good grasp of what this is. It's not too much more complicated than Bayes' rule. You just have to remember, wherever you have a continuous random variable, you simply use density instead of mere probabilities. Okay, that's it. Okay, so this x given y equals y naught, you can think of it as a conditioned discrete random variable, conditional random variable, right? So distribution of x given y equals y naught. So this can help you in classification, making decisions and all. Okay, so now once you have conditionals and all that, you can even think of independence, right? X and y are jointly distributed. When are x and y independent? Okay, this would happen if the conditional is independent of x. If the conditional is independent of x, even the probability for the discrete random variable given the continuous random variable is also equal to the original probability. All of these things work out when you have independence. Remember, independence will be if the conditional distribution of y given x equals x is simply independent of x. That is independence. Okay, so you can define all these things for situations where one is discrete, the other is continuous also. Okay, so when both are discrete, all these are very standard. You just have formulae relating all of this. When one is discrete, the other is continuous also. One can write down formulae like this. Okay, so it's one thing to see this formula. You have to see this in action. So what I'm going to do is solve a few problems which has one continuous random variable, one discrete random variable. The joint distribution is described. How do you find these kind of probabilities? Let me do a few problems for you. Okay, so we're going to start with a simple problem where x is uniform. Once again, these braces indicate that this is discrete, taking -1 with probability half and 1 with probability half, and two conditional distributions are given to you, and you have to find the distribution of x given y equals -1, y equals 1, and y equals 3. Okay, so you can see that y given x equals 1, remember this is indicating that this is a continuous random variable. Okay, right, and this is continuous density, -2 to 2 uniform, and this y given x equal to 1 is an exponential density with 5. Okay, I like to plot these things. I think it's sort of illustrative to plot them, plot the densities, the conditional densities at least, right? So you have -2 to 2 uniform, that's one density. Okay, so clearly you can see I've not drawn it properly, so let's draw it. Okay, -2, this could be +2, this is 1/4 height, right? So this is the conditional uniform -2 to 2, and then you have the conditional y given x equals +1, and that is exponential 5. So exponential 5 is what is the density? It's 5 e power minus 5x, right? That's the lambda e power minus lambda x is the density. So this will probably go down like this. So it'll start at 5. Okay, so it'll start somewhere way out there, 5. And then the density at even 1 has become 5 divided by e power 5. E power 5 is 2, 2 power 5 is already 0.6 or something. It's gone below this. So by the time it hits 2, it will be really, really, really below this. So it will go like that. Okay, so this is 5 e power minus 5x. Okay, so notice when x is 1 itself, it's crossed it. You can find out when it will be 1/4. It will be somewhere around there. Okay, so that's how it goes. But it'll keep going. Right, so these are the two conditional densities, and if x of course takes value -1 and +1, that's sort of not too relevant. Okay, so these are the two conditionals. Hopefully you can picture this now. Okay, so x takes value -1 and 1. When x is -1, y is uniform from -2 to 2. When x is +1, y has a conditional density which is like this. Okay, so x is uniform -1, 1. So what's being asked here is x given y equals -1. Okay, so this is what's being asked here. Okay, so when x given y equals -1, it might possibly take values -1 and +1. So for this, I want to compute probability that x equals -1 given y equals -1. Okay, so for this, I know I need my marginal of y. So let's write down the marginal of y. It's going to be half probability that x equals -1 times the uniform distribution, 1/4, right? Remember, you have to be very careful here. This 1/4 is when x is between, this 1/4 is when y is between -2 and 2, right? So this is when y is between -2 and 2. Okay, and then plus you have probability. So this kind of a thing is a bit difficult to write down. So let me write down the formula first, and then we'll write down. So fy given x equals -1 of y plus half fy given x equals +1 of y. Okay, so now this you can sort of describe. So this is actually 1/4 for y in -2, 2. This guy is 5 e power minus 5x.
but that's, I'm sorry, minus y. Okay, forgetting my x's and y's here. I'm sorry about that. And that's for y positive. Okay, so how do you combine these two and write? So you say it's half times 1 by 4 plus half times 5e power minus 5y for, no, I'm sorry, this is a slightly more complicated density to write down. It is 0 for y less than minus 2. Okay, it is half into 1 by 4 for y between minus 2 and 0. It's half into 1 by 4 plus 5, no, half 5 e power minus 5y for y between 0 and 2. And then it is, I'm running out of room here, so maybe I should stop this somewhere here. Okay, so that's good. That's much better. And it's half 5 e power minus 5y for y greater than 2. Okay, so notice how I wrote that. The first formula is generic. Okay, but then these conditional densities have a certain range for y. Only for y have a certain support, right? Y between minus 2 and 2, this is 1 by 4. Outside of it, this is 0. Only for y greater than 0, it is 5 e power minus 5y. Outside of it, it's 0. Okay, so when you write it down totally, you'll have to say y less than minus 2 is 0. Y between minus 2 and 0, it's half into 1 by 4. And then from 0 to 2, both of them will be active, right? And then greater than 2, only this exponential PMF will be active. So that's the marginal distribution of y. Okay. So now what's probability of x equals minus 1 given y equals minus 1? You know from the formula, it's px of minus 1 times fy given x equals minus 1 of minus 1 divided by fy of minus 1. Okay, so this is the formula, right? So now what is px of minus 1? That's half. What is f of y given x equals minus 1? That is just 1 by 4 between minus 2 and 2. And what is y value here? It's minus 1. So evaluated at minus 1, I'm going to be 1 by 4. Okay. And what is fy at minus 1? You see it's half into 1 by 4. And that is 1. Okay. So notice this becomes 1. Okay. Okay. So you can also check that probability that x equals minus 1 given y equals, x equals plus 1 given y equals minus 1 is px of 1 times fy given x equals plus 1 of minus 1 divided by fy of minus 1. So now notice this, the first thing is half, the next one is 0, right? The conditional distribution of y given x equals plus 1 is the density, exponential density, and at minus 1 it is 0. Okay, so it's half into 0 by half into 1 by 4, and that's 0. Okay, so the conditional density of x given y equals minus 1 is actually, there is no distribution here, it's a constant. It's equal to minus 1 with probability 1. Okay, now that makes a lot of sense, right? So look at this plot. If y were to be minus 1, if y were to be minus 1, clearly x has to be minus 1. Okay, there's no way, if x is plus 1, there's no way y is going to be negative. Okay, so this works out so easily. Okay, so that's clear. Now let's look at the slightly more interesting case. This is when y is equal to plus 1. So in this case, I'm going to cut short a lot of this formula and then write directly what I would get. Okay, so it's probability that x equals minus 1, that's half, okay, times the conditional density evaluated at 1, so that's going to be 1 by 4, plus, no, there's no plus, it's just 1 by 4, right? So it's the conditional density of y given x equals minus 1, that's the uniform density evaluated at plus 1, so that's just going to be 1 by 4, okay? Now divided by the marginal density evaluated at plus 1, right? So the marginal density evaluated at plus 1 is going to be half 1 by 4 plus half 5 e power minus 5. So that's the formula for x equals minus 1 given y equals 1. Okay. So notice probability of x equals plus 1 given y equals 1. Okay, you can go through and do the formula if you want, but a quicker method will tell you it's just 1 minus this. Right, it's 1 minus probability of x equals minus 1 given y equals 1. Why? Because this is a is a proper distribution, right? It's a proper random variable. Given y equals 1, x takes only two values, minus 1 or 1. Once you find the probability it takes one value, probability it takes the minus value. Other value is just 1 minus that. Okay. So if you do that, you will simply get, or you can use the formula again if you don't like that method. You're going to get half phi e power minus phi by half into 1 by 4 plus half into 5 e power minus 5. Okay. Right? So you see how that formula sort of works to give you the conditional distribution for the discrete given the continuous random variable took a particular value. Okay. The last one is x given y equals plus 3. Just by inspection, if you got a value of plus 3, x could never be minus 1, right? So you can quickly see probability of x equals minus 1 given y equals 3 is actually 0, and probability of x equals 1 given y equals 3 is 1. Okay. So hopefully this example showed you how to apply that Bayes-like formula for conditional probabilities of discrete given continuous. Okay, so the continuous given discrete ends up being a density, but the discrete given continuous, you can use Bayes-like formula using density instead of probabilities. Okay. All right. So this is the first problem. Here is another problem. Okay. So this is sort of a word problem, but let's look at the description. So there is a country, and it says in the age group of 45 to 50, 60% of the adults are male and 40% are female. Not a very good sex ratio in the country, right? Okay, it's all right. It's not the question. So what the question asks is, it says the height in centimeter of adult males in that age group in that country has a normal distribution. 160 is the mean, and 10 is the sigma. Okay, and that of females is normal with mean 150, and okay, so normally when I write normal, we would take it as mu and sigma squared, right? So one needs to be careful here. Okay, so I'm going to take this as okay, so I should be careful here. So let me reword this. So I don't want the sigma squared to be 10. So I'll say sigma equals 10. Okay, so I'll change this so that it's convenient. So I'm remembering now that in one of the previous slides I did the same thing, but let me go back and make sure I get that right. So here also we will take sigma to be equal to 0.4 and sigma to be equal to. Okay, so in a question, if I want sigma square, I'll mention that sigma square. So here I'm assuming this is mu equals 0.6. Mu is there, and then sigma is 0.7. Okay, so I forgot to mention that. Normally, I think a lot of people use sigma square there. I'm going to take sigma for these problems just for convenience. I mean, if it's sigma square, it's complicated. Okay, I mean, it's okay. You could take sigma square also. It's not a big deal. Okay. Okay. So this is the distribution that's given to you. So a random person is found to have a height of 155 centimeters. So is that person more likely to be male or female? Okay. So what is the question here? So X is the, let's say, is the sex of the person. It takes two values, male, female, male with 60% probability and female with 40% probability. That's the distribution of X. Okay, so I should say this is distributed like that. Okay, so now Y is the height. Given X equals M, Y is normal with mean 160 and sigma equals 10. Okay, and Y given X equals female is normal with 150 comma sigma equals 5. So you know the distribution, right? So Fy given X equals M of Y is 1 by root 2 pi into 10 e power minus Y minus 160 squared by 2 into 10 squared. Okay, so that's the distribution. Fy given X equals F of Y, you know, you can write likewise. Okay, so it's just instead of 160 you put 150, instead of 10 you put 5, you will get the conditional density. Okay, so both of these are given. One can also write down Fy of Y. Okay, I'll write it down below when I write the final answer. You can see how to write that, right? It's going to be 0.6 times the first density
plus 0.4 times the second density. That's Fy given y. So the question is asking for x given y equals 155. What is the distribution here? Okay, and in particular it's asking, is that person more likely to be male or female? Okay, so here what one can do is try and find probability that x equals m given y equals 155. Okay, let's try and evaluate that. So that's going to be 0.6 times the conditional evaluated at 155 given x equals m. So that's going to be 1 by root 2 pi 10 e power minus 155 minus 160 is 5, so 5 squared by 2 into 10 squared. So that's the formula here. Okay, divided by, you're going to write the Fy evaluated at 155, that's going to be 0.6, the same thing, 1 by root 2 pi 10 e power minus 5 squared by 2 into 10 squared plus 0.4 times 1 by root 2 pi. The resolution is not good enough. 5 e power minus, once again, it's 155 minus 150, isn't it? That's 5 squared by 2 into sigma squared, which is again 5 squared. Okay, so one can simplify this and you will calculate a probability. So what will be probability that x equals f given y equals 155? If you want, you can write it down. It's just 1 minus this other probability. Okay, it after all takes two values. So you find this value. Whichever is greater, you will pick that. Okay, so that's the problem here. So you notice how some sort of a classification problem can be solved by assuming a model like this, right? So given a model like this, in this model, the classification problem will have a precise sort of calculation that you can do. Given the height, you'll plug it into this formula and see which is a greater probability, and you'll decide. In fact, there's only two possibilities, right? If one of them has a probability greater than 0.5, that's going to be the larger one. So you can just calculate one and check if it is above 0.5 or not. Okay. So hopefully I've not written down the final answer for you. I'll leave that as an exercise. Go ahead and compute this final answer. Okay. So you see how in a sort of semi-realistic situation, these kind of discrete continuous models enter the picture. Okay. So these are very useful to know and understand. Okay. So here's the last problem in this sequence that I'm doing for you. Slightly different. So here again you have a discrete random variable and a continuous random variable, but here I'm not going to directly give you the conditional density. I'm going to give you the conditional density indirectly in terms of a relationship involving the random variables. So that's what is done here. Okay, I'm defining a random variable y to be equal to x plus z. X is a discrete random variable, uniform -3 -1 1 3, and z is a normal random variable, mean 0 and variance sigma square. So this is like, this is variance equals sigma square. I apologize for this, not being very consistent here, so I should be very careful. So normal distribution, usually one writes mu and sigma squared. In the previous two problems, I just simply took it as sigma plus, forgive me for that, you should take it as sigma squared. Sigma squared is the most standard notation. Okay, so I'm going to define y as x plus z. Okay, and the z, when x is uniform -3 -1 1 3, and z is normal 0 sigma square, and these two are independent. Okay, x and z are independent. Now the question asks, what is the distribution of y, and find the distribution of x given y equals 0.5. Okay, so the trick is to find, okay, so x distribution is given to you. The trick is to find fy given x equals -3, for instance. Okay, so what is going to be the density of y given that x is -3? Okay, see, remember, so how do you do this? So y given x equals -3 is actually -3 is the same as -3 plus z. Okay, z is normal with mean 0 and variance sigma squared. What is -3 plus z? Okay, you remember you have to use now the functions. It's just translation of a random variable. It's just a shifting of the PDF. The density just shifts to -3, and in particular for the normal, we know that this is going to be normal with mean -3 and the same variance sigma squared. Okay, so it's just a shift. Okay, remember the translation. I did this example quite often, quite some detail when we did functions of a continuous random variable. So you get this. So this is the sort of the crucial step here. So when you say x is -3, y simply becomes -3 plus z. Okay, z is the random variable, and then this is just -3 plus z, right? So that's what's important. The reason is x and z are independent, right? So there's no dependence between. So because x took a -3 value, z is now suddenly not going to change. It's going to be just -3 plus z. The same thing you have to sort of see for the other ones. Okay, so think about why this is true. So you can sort of convince yourself, and this will be just normal -1 sigma squared. Y given x equals 1 is just normal 1 sigma squared, and then finally y given x equals 3 is normal 3 sigma squared. So once you do this, you're back to familiar territory. What is the distribution of y? So this is the crucial step. This crucial step is this, understanding the conditional distributions. Once you got this, the rest is same as before. So notice the trick here. The trick here was, instead of specifying the y given x equal to -3, y given x equal to y minus 1, etc. explicitly, you give a function involving x and another random variable z. Okay, then expect you to evaluate that function. Okay, so here's a little exercise. In this exercise, I'm going to say x is same uniform. Let's say -3, -1, 1, 3. And z is normal 0 sigma squared. These two are independent. Okay, and then I'm going to say y equals x times z. Instead of saying x plus z, I'm going to tell you x times z. Okay, so this is an exercise for you. For this problem, if y is x times z, what is the marginal distribution of y? What is the the conditional distribution of x given y equals 0.5 or anything else like that? Okay, so here also the problem boils down to that. You'll have to find y given x equals -3. Okay, and you'll see it's just x times z, so it's -3 times the distribution of so it's -3 times z. Okay, so y given x equal to -3 is just -3 times z, and that is normal -3 sigma squared. Okay, so this is important to understand. Okay, so this is the last problem that I wanted to do, and you can see the sort of flavor of the problems here. So this kind of problems are very very natural in reality. Even this one is actually, this problem is actually a very common model in many communication systems. So people use this model in many systems. So it's very natural that a discrete random variable and a continuous random variable together have some joint distribution because of whatever happens in practice. Okay, so how to describe that, how to deal with that is very important, and this can help you a lot in classification, in particular the reverse question, right? Observe the continuous random variable and what can you say about the values taken by the discrete random variable. Okay, so I'm going to stop here for this lecture. We'll pick up from here in the next one. Thank you.